So let's investigate some more laws of probabilities that we can use to explain genetic events. So as we discussed previously, the product law is used when the outcome of the first trait is unrelated to the outcome of the second. So another example of this would be looking at the chance of flipping a head on both a penny and a nickel at the same time. In this case, all four combinations have an equal probability. You could flip a heads on the penny and a heads on the nickel. This would be a 1/2 chance times 1/2 chance. You multiply those together and that would give you a 1 in 4 chance, or 25% chance. You could flip a heads on the penny and a tail on the nickel. You could flip tail on the penny and a head on the nickel. Or you could flip tails on both. And if you do the math for these, what you can see is that all four combinations have a 1 in 4, or 25% probability. That's equal probability. Okay, in this example, the second example, let's say if you have two children, what is the chance of having a boy and then a girl in that particular order? So the first possibility is that you could have a boy first. That's a 50% chance. The second possibility is you could have a girl second. That would be a 50% chance. Each of these would be an independent event. Just because you had a boy first doesn't necessarily mean you're going to have a girl second, doesn't necessarily mean you're going to have a boy second, and so on. So each of these would be a 50% chance. You have a 50% chance of having a boy first, and a 50% chance of having a girl first, or a 1 in 2 chance. You have a 1 in 2 chance of having a girl second, and a 1 in 2 chance of having a boy second. So in looking in this particular order, your chance of having a boy first would be 50%, or 1 in 2. A girl second would be 1 in 2. And so the overall chance of this happening would be 1 in 4. The other possibilities is that you could have a boy first and a boy second. That's equally likely, 1 in 4 chance. Another possibility is having a girl first and a boy second. That's a 1 in 4 chance. The other possibility would be having a girl first and then a girl second, which would also be a 1 in 4 chance, or 25% chance. So a sum law is used to calculate the probability of a generalized outcome that can be accomplished in more than one way. So what it states is that the probability of obtaining any single outcome, where that outcome can be achieved in 2 or more different ways or events, is equal to the sum of the individual probabilities of all such events. So that's a little bit wordy. Let's go through some examples. Using our previous example of flipping a penny and a nickel, what would the chance be of flipping a penny and a nickel and obtaining one head and one tail? In this case, we don't care if it was the penny or the tail that was the heads. So as we saw previously, there were 2 ways this could happen. You could have the penny as the tail and the nickel as the heads, or vice versa. Each one of these carried a probability of 1 in 4. So according to sum law, all you'd have to do is add these 2 together. So 1 in 4 plus 1 in 4 equals 1/2, or 50% chance. Let's do another example. If you're having 2 children, what is the chance of having 1 boy and 1 girl? Now remember, you don't care about what order this happens in. So as we said before, there are 2 ways this can happen, both of which have a 1 in 4, or 25% chance of happening. You could have a boy first and a girl second, or you could have a girl first and a boy second, each of which has a 1 in 4 probability of happening. The other 2 that we don't care about in this particular case would be if you had 2 boys and if you had 2 girls. So if you had a boy, at least 1 boy and at least 1 girl, adding these together, you're going to have a 1 in 2 chance, or a 50% chance of having 1 boy and 1 girl. The binomial theorem is used to calculate the probability of any specific set of outcomes among a large number of potential events. So when you're looking at small numbers, like 2 children or 2 different coins that you're flipping, it's not that big of a deal. But if you're starting to look at maybe, say you have 10 kids, and what is the chance of having 10 boys? Okay, it starts to get a little bit more complicated when you're doing the math, and then probably the best way to answer something like that is to use this binomial theorem. So a general binomial theorem is a plus b to the nth power equals 1. And in this case, A and B are the respective probabilities of the 2 alternate outcomes. N equals the number of trials. So in this case, A, say we're talking about boys and girls, A would be the number of, the chance of the boys, this would be the chance of the girls, to the n power would be the number of children that you would have. And so if you look in your book on table 3.2, you can use Pascal's triangle to help you figure out the coefficients for any of the different outcomes. So using an example, let's just do 4 children. Let's say in a family of 4 children, what is the probability that 2 will be male and 2 will be female? You don't care what order they happen in. Each birth is an independent event, and you can get multiple birth orders that can achieve the same general outcome, right? You could have 2 males first and then 2 females. You could have 2 females first and then 2 males. You could have a boy, girl, and so on. So if you look at Pascal's triangle, you can write out the expanded binomial for n equals 4. In this case, it's a to the 4th plus 4a to the 3rd b plus 6a to the 2nd b to the 2nd plus 4ab to the 3rd plus b to the 4th. What these numbers correspond to, okay, the first one could be 4 boys. The second one would be 3 boys and 1 girl. The second would be 2 girls and 2 boys. This one would be 1 boy, 3 girls. This one would be all girls. Those are the different possibilities you could have if you had 4 children. So in this case, we want to know how many, what the probability of 2 boys and 2 girls, so, or the term 6a squared b squared. So the probability of this outcome, putting in the chance of having a boy is 1 in 2 or 1/2. The chance of having a girl, 1 in 2 or 1/2. So it would be 6 times 1/2 squared times 1/2 squared. You could combine those terms, 6 to the 1/2, 6 times 1/2 to the 4th, or 6 times 1 in 16th. This gives you 6 out of 16, or you could simplify it to 3 out of 8 chance of this happening. Okay. When you start to look at chances for something happening over a very large population, you may have some deviation from the expected ratio, and this can be completely reasonable. For example, say you were looking at coin flips and you were to toss a coin 1,000 times. You would expect about a 1-to-1 ratio of heads to tails, so 500 to 500. Would you be surprised if you saw some different numbers? For example, what would have happened if you would have 498 heads to 502 tails? Was that reasonable? What about 400 heads and 600 tails? Do you think that's reasonable? Or do you start to think, maybe there's something wrong with this coin? Maybe it's weighted on one side. How about 1,000 tails and 0 heads? How likely would that be? Or do you think maybe there's something wrong with your coin? So what you can do is you can use chi-square analysis to determine what predicted outcomes would be reasonable or not reasonable for a given outcome. So what you can do, first assume that your data is going to fit a given ratio, such as a 1-to-1 ratio, talking about, say, children being boys or girls, a 3-to-1 ratio, we're talking about our standard inheritance dominant recessive, or a 9-to-3 to 3-to-1 ratio if we're talking about the dihybrid traits. We can call this our null hypothesis. And what we can say is any difference that we see is attributed purely to chance, and the formula for this, chi-squared equals the sum of the difference between the observed result minus the expected result squared over the expected result. Okay, so what we're really looking here is how much do our results differ from what would be expected. Okay, so let's do an example here. This is from the book. Let's say you have a cross. It's you would expect a ratio of a 3-to-1 ratio. And so let's say you had 1,000, whatever that you're looking at, okay, pea plants or something. Let's say 740 of them had the dominant and 260 of them had the recessive. Okay, what you would expect is a 750 to a 250 ratio. So you need to calculate the deviation from that expected. And so you just subtract the 740 that you observed minus the 750 that you expected. For this one, it would be the 260 you observed minus the 250 expected. For both of these cases, you're off by 10. So when you're calculating this, you need to square it. You need to square that deviation. So in both cases, it would be 100. Now, both of these numbers you need to divide by the expected. So you've got your 100 divided by 750 in this case for the first one, 100 divided by 250 for the second case. Okay, so you have 0.13, 0.40. You add those together, your chi-squared value is 0.53. I'm going to talk about this p-value in just a second, but what I'm going to show you with a dihybrid cross, the numbers, you're going to end up in this case with the chi-squared value of 4.16. The expected versus the observed, you can subtract those out, you can square them, divide them by the expected, and that's going to be your total numbers here. Okay, so the next step is now to interpret that chi-square value. The first thing you need to do is determine what we call the degrees of freedom. The degrees of freedom are defined as n minus 1. N is the number of different categories into which the data are divided, or number of possible outcomes. So for example, when we're talking about our 3-to-1 ratio, there's two possible outcomes, right? They could be dominant or they can be recessive. So in this case, n equals 2. So your degrees of freedom, since it's n minus 1, you'll have 2 minus 1. Your degrees of freedom equals 1. In the 9-to-3 to 3-to-1 ratio, there's 4 possible outcomes or phenotypes. So in this case, n equals 4. So n minus 1 equals 3. Your degrees of freedom would be 3. So what you would do next is then go to a table. There's a table in your book, and any statistics book could also give you this particular table. When you look at it, you have to find your degrees of freedom on the left. Okay, so in this case, with the first one, we had 1 degree of freedom. You find out what the chi-square value is. Okay, in this case, it was 0.53, so it would fall in between this number and this number. Another way to look at it is to look at this particular chart. You've got your chi-square value was 0.53, so about here. Okay, you can go over and read its probability on the chart. That was what it gave us as a p-value. In this case, p was 0.48. Okay, so what this means is that this is likely to happen by chance. If you fall into any of these dark blue colors, this is something that would fail to reject the null hypothesis, meaning that most likely your hypothesis was correct. You can't say for sure that it was correct, you can just say that your data support your hypothesis. If you're in this light blue area, what you can say is that you have to reject the null hypothesis. It is unlikely that this happened by chance. In this case, if it was 95% likely to happen, only 5% of the time would it happen by chance. In this case, 1% of the time it would happen by chance. In this case, 0.1% of the time it would happen by chance. So that's pretty unlikely. 99.9% of the time, there is some reason why that difference appeared. Okay, so let's do a couple more practice problems at the end of this section.